Suppose 83% of Americans are right-handed. If we randomly choose 4 Americans and we wanted to find the probability of selecting exactly X right-handed Americans, this represents a binomial situation. So choosing X number of right-handed Americans, we could choose exactly 0, exactly 1, exactly 2, exactly 3, or exactly 4. So those are only possibilities for our random variable X. So a binomial situation for discrete random variable X, there's a few stipulations. The first one is there's a fixed number of trials n. So in this case, n is 4 because we're only choosing 4 Americans. The second stipulation, there's only 2 possible outcomes for each trial, and we can classify those outcomes as a success or a failure. So we will define a success, in this case, to be choosing a right-handed American on any single trial. So every time we choose someone, we're going to consider a success if we chose a right-handed person. Failure will be the complement of success. So whatever we choose that is not a right-handed American, that will be considered a failure. So it is up to you to define what a success and a failure is. Okay, so number 3, the third stipulation, on any trial, the probability of success is P, and the probability of failure is 1 minus P. And sometimes you will see 1 minus P written as Q, and I will actually do that sometimes also. So instead of 1 minus P, I'll put a Q. The probability of a success, in this case, is 0.83. So on any single trial, when you randomly choose an American, the probability that they're right-handed is 0.83. Probability of failure, meaning they are not right-handed, will be 0.17. And then the last stipulation is that the trials must be independent, meaning P and Q, or 1 minus P, remains the same for each trial. Now in this case, because we're looking at choosing Americans, there's over 300 million Americans, so the probability is not going to change drastically enough when we're choosing out of 300 million people. Now if you only had 20 or 30 people you're choosing from, then you wouldn't be able to treat these as independent. But in this case, the population is large enough that we're choosing from that we can assume they are independent. Okay, so back to this example. If we have 83% of Americans right-handed, we choose 4 Americans, we want to find the probability that none are right-handed. Well, if none of them are right-handed, we want to think about what has to happen when you choose the 4 people. The first one has to be not right-handed. The second one not right-handed, and so on. So this is a straightforward multiplication rule. The probability of the first one is not right-handed is 0.17. Now I'm using L for left-handed, so I'm just going to assume here to make it easy, we have right-handed or left-handed, not considering the ambidextrous, where they could be either. So we're just looking at right or left-handed here. So the first one being left-handed is 0.17, the second one 0.17, and so on. So that is 0.17 to the fourth, which is 0.008. So if you choose 4 Americans, the probability that none are right-handed, same as saying all are left-handed, is 0.0008. Okay, which is less than 1%. Okay, so it's a very small probability. Okay, the next one, all 4 are right-handed. So what has to happen there is you have to get 4 right-handed. So similar to the last case, except now you have 0.83 because they're all right-handed. 0.83 to the fourth is 0.4746. So it's almost a 50-50 or 50% chance of getting all 4 right-handed. Now that's a lot higher probability than all 4 left-handed because a much higher percentage of people are right-handed. So you should expect that you're going to have more right-handed people than you are left-handed. Okay, so the The probabilities in those two parts are fairly straightforward calculations found by just applying the multiplication rule for independent events. There was only one way we could choose 0 right-handed people, meaning left, 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 and only one way to choose 4 right-handed people, meaning right, 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 right. Okay, so if we go along to the next page. Okay, so we just looked at getting exactly 0 or exactly 4 right-handed people. Well, now we have to look at getting exactly 1, 2, or 3 right-handed. So now we have to pay attention to exactly how we can get n right-handed Americans. So meaning 1, 2, or 3 right-handed Americans out of the 4. I probably should have used an x there instead of n. Because n is really 4 because we're choosing 4 Americans. But we want to look at x being 0, 1, 2, 3, or 4. Okay, so if we look at exactly 1 right-handed, we need to think about how can we get exactly 1 to be right-handed. Well, it should make sense that when you choose 4 people, to only get 1 right-handed, the first person could have been right-handed, or the second, or the third, or the fourth. And then the other 3 would have to be left-handed. So if you look at the different sequences of how you can get exactly 1 right-handed, the first is right-handed, then the last 3 are left, or the first one could be left, the second one right, and the last 2 left, and so on. So there are 4 different ways to get exactly 1 right-handed. So what we need to look at is we can have that first sequence happen, or the second. Okay, so the first one, or the second, or the third, or the fourth. So this now turns into a combination of the addition rule and the multiplication rule. We use the multiplication rule to find the probability of each sequence, but then those 4 sequences could have happened. So we have to add the probabilities together of each sequence. Okay, so when we go through and find the probability that you get right, left, 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 0.83 is the probability of the first one, and then 0.17, 0.17, 0.17. Okay, so the second one is 0.17 times 0.83 times 0.83. I'm sorry, I just said that wrong. 0.17 times 0.83 times 0.17 times 0.17. Okay, and what you want to notice there is, notice how you only have 0.83 once, and then you're multiplying 0.17 3 times. So you can shorten that up to saying each sequence has 0.83 times 0.17 to the third probability. So the total probability, so the probability of exactly 1 right-handed person will be 4 coming from the 4 different sequences, times 0.83 times 0.17 to the third. So that'll be the total probability, which is 0.0163. Okay, and then if you look at exactly 2 right-handed, so now you can have the first 2 right-handed and then the second 2 left-handed, and then you could have right, left, right, left. And if you go through and list out all of those sequences, now you'll see there are 6 of those. Okay, there's 1, 2, 3, 4, 5, 6 ways that you can get exactly 2 right-handed. Now the probability of each sequence, there's 0.83 twice and 0.17 twice. So no matter how they were arranged, as long as you have 2 R's and 2 L's, you're going to have 0.83 twice and 0.17 twice. So each sequence has a 0.83 squared times 0.17 squared probability. But now again, the issue is that happens 6 times. So if you add that together 6 times, you do 6 times 0.83 squared times 0.17 squared. And when you do that, the probability of exactly 2 right is 0.1195. And I just want to point out that sometimes you'll see this once you define the success to be a right-handed person. You might see it written like this: probability of 2 equals 0.1195. And it's implied there that it's 2 successes, which we already defined to be choosing right-handed Americans. For 1 right, you would say P of 1 equals 0.0163. And you can even see it written as like probability that X equals 1. So you could see X equals 1 in the parentheses, X equals 2 in the parentheses here. Those are just different notations that you may see. Okay, so the probability of exactly 2 right-handed Americans, if you choose 4, is 0.1195, so almost 12%. Okay, and then similar, trying to find exactly 3 right-handed people, you go through and list the sequences. Okay, so you list the sequences and then the probability of each of those sequences. You have 1 left-handed and 3 right-handed. Essentially, it's the same idea as 1 right-handed, but you just flip-flop the L's and the R's, and that'll give you exactly 3 right-handed. The only difference now is you have 0.83 to the third, because you're multiplying it 3 times by itself, and 0.17 once. So in that case, each of those probabilities has a 0.83 to the third times 0.17 to the first probability. So the total probability will be 4, because there's 4 of those sequences, times 0.83 to the third times 0.17 to the first. So the probability of 3 right is 0.3888. So about almost a 39% chance that exactly 3 will be right-handed. Okay, now the last thing I'm going to show you here real quick is the probability distribution that would go along with this example. So remember that a probability distribution is X and P of X. X represents the number of successes, or the number that your random variable can take on. In this case, you can have 0, 1, 2, 3, or 4 right-handed Americans. The probability of exactly 0 is 0.0008, and that was found on the first page. Okay, right here, 0.0008. All 4 was 0.4746, so that's where the last number comes from here. And then the 1, 2, and 3, we found those on this page. Okay, so that is what the probability distribution will look like for that example. One thing you want to notice is, because we have all the possible values for X listed out, the sum of the probabilities, when you add them all up, the probabilities, you should get 1. Now, because of rounding, it might be slightly off, but it should be extremely close to 1 with rounding. And then the mean, mu, of the probability distribution is the sum of X times P of X. And if you do 0 times 0.008 plus 1 times 0.0163, and so on, you get 3.32. The other way you can find the mean using your calculator is put your X values in list 1. Okay, so put these in list 1. Put your P of X in list 2. And then calculate the 1 bar stats on L1, L2. So your frequency list will be P of X. And that should give you 3.32.